morning. So it's a great pleasure to present Professor Charles Newman from Courant Institute, and he is going to speak about Brownian web.
Thank you very much. I'm always pleased to be in Rio and at IMPA. In fact, I was here only 4 months ago, but I'm happy to be back again. I think there's a real affinity between New York and Rio for various reasons. Of course, I think IMPA perhaps plays a bigger role within Rio and as a center of mathematics than Courant Institute does within New York. In Rio, there's at least some fraction of taxi drivers, if you tell them you're going to IMPA, will know where to go. I don't think there's probably any taxi drivers in New York. On the other hand, just to give you an idea that mathematics is of some significance in New York, I'm not sure this will be able to be seen very well, but I have a transparency from a supermarket advertisement in the New York Times from 2 weeks ago, which demonstrates that mathematics does have some cultural significance. I guess this would be called a supermarket metric. That's an actual advertisement from 2 weeks ago.
Is the market still alive?
I don't know. They must be desperate. They're trying to attract mathematicians. And okay. Well. So the Brownian web, which is the subject I'm going to talk about, arises in scaling limits of coalescing random walks. So I want to try to convince you that coalescing random walks are an extremely natural object. Let me explain what this diagram, how this diagram, which is a simulation, is generated. In fact, the best way to start is perhaps to rotate it somewhat. So think of this as a piece of Z2, and at every site of Z2 you toss a fair coin independently, and if it comes up heads, then you draw an arrow from that site going upwards to the next site, and if it comes out tails, you draw an arrow going right to the neighboring site. So for example, let's see if I can, is there a pointer for the, let me try to do it here. So for example, at this location, I guess the coin toss was a heads, and therefore there's this arrow going up. At this location, the coin toss was a tail, so there's an arrow going to the right. And you just do that independently at every site, and here's a piece of what you come up with. Now let's rotate it, and I want to rotate it now by, I guess, 45 degrees. Which way depends on how you like to draw space-time diagrams. So I prefer drawing them this way. So in my case, this will be space and this will be time. And now suppose you follow one of the paths. Thank you. Suppose you follow one of the paths, let's say starting from, I don't know, here. Then there was a choice made, a coin was tossed, and you and that choice corresponded. So now time is going up, and this is space. So a choice was made, and the choice corresponded to moving left 1 unit in 1 time step. And then another coin was tossed over here, and the choice was made to move left again in a 1 time unit. Another coin was tossed, the choice was made to move right in 1 time unit. So if you follow a particular path, just following the arrows, like this, that is the space-time path of a simple random walk. Each time step you toss a coin, you move to the right in the next time unit, or you move to the left in the next time unit with probability half. That's true for any path that you follow in this diagram. On the other hand, because the coins were associated with space-time points, when two paths meet, like this one meets this one, then since from then on you use the same set of coins, they automatically coalesce. That is to say, they then follow the same path. So this now is a diagram of not just the path of a single random walk, but a whole bunch of random walks, which when they meet automatically coalesce. That is, the random walks are independent until they meet, at which time they become the same walk. And you can also see here it automatically happens that there are random walks kind of starting from all kinds of locations, right? There's one that starts from here. There's no sort of precursor to that walk. It just begins over here. And other walks, which say one from here, there was something before it which led up to it. This is just a elementary construction which automatically gives you coalescing random walks. Anything which arises in such a simple way has to be a kind of natural object. And now what we want to do is study the scaling limits of these objects. So scaling limits of individual random walks are well known. Instead of thinking of the spatial separation as one unit of space and the time as one unit of time, scale the space and time variables so that the time scaling is you scale space by delta and time by delta squared, or the other way around, whichever is right. So in time delta, you should move in space delta squared, I guess. So scale space by delta squared, time by delta, and that shrinking with delta getting very small. An individual random walk path under that space-time scaling, its distribution converges to that of Brownian motion, a much studied and important subject, not only in financial mathematics. And what we're basically interested in talking about today is what happens when you do such a space-time scaling, not on individual paths, or even on several paths at the same time, which would clearly go from finitely many coalescing random walks to finitely many coalescing Brownian motions. But somehow we'd like to understand the scaling limit of all of these walks together, all these walks starting from all over in space-time. A priori, that sounds somewhat complicated, because if you just look at it, if you look at these graphs as a subset of space-time, and the limit will just be everywhere. So the question is, how do you formulate things so you have a somehow natural object to study? And that's basically the subject I want to talk about, which is that limiting object is what we've started calling the Brownian web. I don't think it has anything to do with the webs that Griffiths talked about in his talk yesterday. I don't think. But you never know. Okay, we'll come back to this diagram in a little while. But before I get to that, I'd like to give you a little bit of the background as to why one might be interested in this. And so this is a kind of diversion from the straightforward presentation of the Brownian web, giving background as to one sort of situation in which it arises, which is in a subject that's called aging in statistical physics. If this will be, because of time constraints, this will be somewhat condensed, maybe not very coherent, but at least may give you a flavor of the point I want to make is that scaling limits in space and time of various kinds of processes, or in time and some variable, which in our case will be a spatial variable, is something that arises naturally, in particular in the phenomenon called aging. And many of us are more interested in aging these days than we were some years ago. So let me describe what aging. If the discussion about aging they don't follow too well, it's okay. We're going to come back to the random walks and the Brownian web, and the aging, as I say, is just background. So aging, or what's called normal aging in the physics literature, is something that happens in out-of-equilibrium systems, as opposed to systems which are sort of far out of equilibrium systems, as opposed to systems which are either in equilibrium or approaching equilibrium. When you look at various quantities depending on two time variables in systems in equilibrium, then they tend to be functions of the time difference. The point of an aging system is that it changes so much as it ages that the natural quantities are functions of time ratios rather than of time differences. So one thinks of an out-of-equilibrium system, which is in some sense born at time 0. It ages until a certain waiting time, and then you observe it during some time interval of length. Let's see, this t, let's see, t prime. During time interval of length t prime after the aging interval. So often in physics literature, you do something to it at time tw, and you measure the response. So you have some kind of response function. But in our situation, we actually won't be doing something to it. We'll just basically start observing it at time tw. We'll observe it during this time interval of length t prime, and some quantity having to do with that observation will be this function r, which depends upon the aging time and the amount of time you look at it after it's aged from birth. And the normal aging phenomenon is that many such functions in out-of-equilibrium systems are asymptotically functions of the ratios of times rather than the time difference. So I like to quote the father of a colleague of mine, Sylvan Capel's father, who some years ago, well, I guess he was in his 70s then, said that at his age, decades go by as fast as years used to. And that's basically, an example of this fact that things should be measured in ratios of how long you've already waited. Okay, so the mathematical issue in some particular example, and I'll give a particular example in a while, rather briefly, is to prove that this is really true in the sense that if you take this function and take a limit in which all the times go to infinity, but with some keeping ratios fixed, that you get some limiting quantity, which is some non-trivial function of the ratio. And the point of aging is that it's closely related to scaling limits. That is perhaps the best way of proving such a result is by understanding some kind of scaling limit. In our case, will be a scaling limit in space and time of some process, and that scaling limit will have certain self-similarity properties, and it's the self-similarity properties of that scaling limit which make this limit be a function of the limiting ratio. And in particular, you can actually express that the quantity that you're interested in, this capital R of this script R of theta, as a functional of the self-similar scaling limit. Today I'm going to talk only about not this first example, which is aging in a certain disordered system, but rather about a persistence in a one-dimensional coarsening model, which is the same in one dimension as the voter model. The voter model is a much-studied model in the probability literature, and is closely related to coalescing random walks. So in fact, we'll immediately start talking about coalescing random walks, which gets us back to the Brownian web. So the point of this is that there's a kind of natural question about aging of persistence quantities in one-dimensional voter models, which immediately leads you to the study of scaling limits of coalescing random walks. So today I'm only going to extremely briefly describe this aging quantity and the voter model, but primarily talk about the scaling limit, which is this Brownian web. And this discussion on aging is there as a kind of background to try to convince you that studying such scaling limits is somehow is a natural physical motivation. So maybe I should at least say in words what the voter model is. I'm just going to, it's a standard fact that I think going back to Ted Harris, that it's closely related to coalescing random walks. So the voter model is the following kind of model, and I'll describe the one-dimensional one since that's what we're talking about. It's a model in which you have at each site, it's a Markov process in time. At each site, on the integers, at each spatial site, you have someone who can, or an object which can be in one of q different states or colors. The most common one is 2, but you can take any q, and in fact the situation in which q equals infinity, which roughly speaking means at time 0, every individual starts as their own color, is also quite a natural object, which is somehow comes up naturally in sort of studying genealogies of family names or things of that sort. And then at random times, sites update, and the way they update is by picking one of their two neighbors at random and taking that neighbor's color. And so you begin with, let's say, the typical thing is you begin with completely randomly chosen colors at time 0, and then as time evolves, people are choosing the colors of their neighbors, so you get larger and larger intervals of the same color, and you watch how those things evolve. And that process is closely related in several different ways to coalescing random walks. And I'm not going to try to explain the relationship because there isn't the time to do that, but it's quite simple and direct. Anyway, so let me, I'll briefly get back to the voter model, but let me go to the coalescing random walks. We want to talk about diffusive scaling limits, namely we scale I guess I had it backward. Anyway, scale space by delta, time by delta squared, time, and we let delta go to 0, and we want to understand those things. There are two ways in which you might try to study that. I'll call it the simpler and the harder way. The simpler way is forget about, for the moment, the diagram I showed before. I'll come back to it in a second. Just think about starting with random walkers, one at each site of the integer lattice. And those walkers are starting at time t equals 0, and now they do independent random walks, except when they meet, they coalesce. So, and no new ones are created. That's the simpler version. So you start with many walkers, one at every lattice site, one at every integer site, and as time goes on, because they're coalescing, you get fewer and fewer of them. And that's, in fact, the aging is that you can see how old the system is by seeing what the density of walkers is, basically, decreases in time. And you can try to understand the scaling limit of that as this parameter delta goes to 0. The harder and some mathematically more interesting one is don't just start walkers at time t equals 0, but start them at every space-time point in the lattice, so that when things coalesce, you kind of create a new walker to replace it. The simpler one is actually the scaling limit of the simpler one is actually sufficient for many aging questions, but for other ones, you'd be interested in this more complete scaling limit. So now let me again go back to that original transparency, or more or less the original transparency, and just re-explain what I just said in using this picture. So what I was calling the simpler scaling limit, you would not look at this entire diagram. You would only focus on the things which started at time 0. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 paths. And as those paths progress in time, some of them coalesce, so the number 10 will go down in time. So here these two coalesced, and here's one here, and this one. Here these three quickly coalesce. This one and this one coalesce over here. But you don't you forget about all these new things which are created in the simpler version. So you only focus on these 10 starting paths and what happens to them as they coalesce, and forget about all the other stuff. Okay? That's clearly a much simpler thing, and that's the scaling limit of that is something which was pretty well understood 20 years ago by Aratia and published, and the other one has also been partially understood, and we have some new approach to it. Okay, so the harder one is the one where you do include everything. You have all these new paths. Basically, at every space-time point, there's always some walker walking. So here's a result of Aratia from his thesis that the scaling limit of the simpler system of coalescing random walks exists, and what you get is something which you sort of know what it should be formally. It should be coalescing Brownian motions. Since you started with a walker, each individual random walk scales to a Brownian motion. Since you start with walkers at every site on the lattice, and the limit when delta goes to 0, the lattice becomes delta z, sort of converges to the real line. So you should get something like coalescing Brownian motions starting from everywhere in the real line. So the point of Aratia's result is that you can make sense out of that, something which corresponds, roughly speaking, to coalescing Brownian motions with one starting from every point of the real line at time 0. T tilde is the rescale time after you've taken the limit. And the reason why you can make sense out of that is because there is so much coalescing going on that all these kind of continuum of walkers at time 0 coalesce to form a locally finite number at any strictly positive rescale time. So that's the crucial point of the Aratia result, that all the complications caused by having Brownian walkers or movers everywhere on the real line at time 0 are sort of instantaneously removed, in the sense that that at any strictly positive time you have only locally finitely many Brownian walkers or movers. So I'll show a kind of simple diagram sort of illustrating that, and then the corollary of this is that for certain aging functions in the voter model, because of its relation to coalescing random walkers, and if you choose in the R so that it's related to this simpler kind of limit, then the script R of theta, this aging function, which is a function of the ratio of times, exists, and you prove it exists by expressing it in terms of the scaling limit process, in particular in terms of a certain random variable depending on this parameter theta, which I'll also sort of indicate. So let me now give you a sort of pictorial version of this Aratia limit. Forget for the moment about these A, B, C, and D. Just look at the blue curves. Actually, blue curves later on are going to become green curves, but never mind. So think of starting with, you kind of start with a sort of blue path starting from every place on the real line at time 0, but as long as you go to a strictly positive time, like over here, then you have a locally finite number. Of course, if this strictly positive time you look at gets smaller and smaller, then the density of these things gets larger and larger, because in the limit somehow they have to be everywhere. But as soon as you go to a strictly positive time, you have locally finite number, and after that, there's no problem in the meaning of this process, because these things simply, each of these blue things is simply a independent Brownian motion, except when the two Brownian motions meet, like here, they coalesce. And there's no difficulty in defining what that means. The only thing interesting about this is that it has a kind of interesting behavior at t equals 0, right? Because you have more and more walkers or movers. So the point of this result of Aratia is that you can make sense out of this, and it's not so difficult because of this. The strong coalescing gives you this locally finite property. Of course, you can't do that in the harder limit because things are created to replace the things that coalesce. So there are always things everywhere going on. So you need to do something a little more sophisticated. So let me just briefly. So this is really a detour to the aging thing, just to give a small flavor. Let me briefly explain how you calculate one of these aging functions. This will be relatively incomprehensible, I'm afraid, but anyway, this will just take a couple of minutes. So here's an example. Here's an example of this quantity R, the thing which asymptotically should be a ratio of times. In the voter model, where you start with everything with a randomly chosen color, and then you look at your neighbors and take on their colors. This is what's sometimes called a persistence quantity. The probability that the individual at the origin does not change at all after you've aged for time tw. Whoops. After you've aged for time tw, it's the probability that there's no change at all for the next interval of time t, or I guess that should be t prime. That's a persistence quantity which should converge to, which the corollary says converges to a function of the asymptotic ratio of t over tw, and that's proven by expressing it in terms of the scaling limit. And there's the expression. It's the expectation within the scaling limit process of Aratia of 1 over q. Q is the number of colors in the model, raised to the random one less than a certain random variable. And now let me just explain what the random variable is. The purpose of this is just to give you a flavor of what a expression looks like in terms of the scaling limit object. So here's Aratia's scaling limit. What is this variable n sub theta? Remember, theta was the ratio of the extra amount of time you observed from the amount of time being aged. So now things have been scaled so that the rescaled amount of time for aging is 1, and then you observe it in the rescaled variable between 1 and 1 plus theta. I don't know how this thing works. Not 1 plus theta. So here's the time interval. You observe the origin during that time interval, and so this quantity has expressed in terms of something having to do with that time-like interval in space-time. And the variable theta is a kind of counting variable. It counts the number of regions of space-time, where regions are things whose boundaries are given by these blue Brownian motions, the number of distinct regions which touch that interval. And so in this particular example, there are 4 distinct regions labeled A, B, C, and D which touch that interval. And that random variable, you then write that specific functional of it, and that is this aging persistence quantity in the limit. Anyway, the point of that is not the formula, but that the reason why scaling, or a reason why scaling limits are of interest is because it's really understanding them and their self-similarity properties. And these things have, obviously, because Brownian motion has nice self-similarity properties on the scaling, also these coalescing Brownian motion things will also have nice self-similarity properties. And it's really those which make the asymptotic, make this function really a limit only of the ratio of times rather than something more complicated. Okay, so that was an example explaining how the simpler type of limit is relevant for aging. But now mainly what I want to talk about is this more complete kind of limit in which you don't only focus on walkers starting at time 0, but all the walkers in that diagram, because that's actually the natural thing that you get anyway. So how do you extend the limit when you have random walkers or Brownian movers starting from every space-time point, and you can't take advantage of the fact that things become locally finite because they don't. I mean, because new things are created all the time. So this more extensive scaling limit has been studied previously. There's an unpublished, unfinished paper of Aratia from '81, which you can get a copy of from him. And there is a paper of several years ago of Toth and Werner, who studied this this Brownian web type object, this object which corresponds to coalescing Brownian motions starting from every point in space-time, because they had a particular application of it to something they call the true self-repelling motion. So there is previous work, and there's also a paper of Sukieluk, Toth, and Werner. There's also a paper of some papers of Tyrelson, which studies this object from a more functional analytic point of view. The kinds of things that didn't exist previously were two closely related things, namely characterizations of the object. That is, can you precisely define the object in such a way, this limiting object, so that you can tell whether or not you have it? Somebody hands you something. Is this that object? Like, how do you know whether you have a Brownian motion? Well, for a Brownian motion, if its finite dimensional distributions have certain formulas, are given by certain independent Gaussian variables for differences of the process at different times, and if you have continuous sample paths, then you know you have a Brownian motion. That kind of characterization result didn't exist, and also convergence results. You know formally what you want the limit of the random walks to be, but there should be, you should have some convergence theorem which tells you that certain functionals or expectations of functionals of the coalescing Brownian walks converge to the corresponding things for the limiting object. And so our basic contribution, I would say, did I say who? I think I had a previous transparency where I said who my co-authors were. I should have pointed that out more clearly. Okay, let me just, for a moment. So this is work that's the work on the Brownian web is joint work with Renato Funches from Sao Paulo, Marco Isopi from Rome, and Krishna Ravi Shankar from SUNY New Paltz. So in order to get characterization and weak convergence results, the first thing you need to do is decide what is this object you're studying, right? In a way, that's the most interesting thing. What is the you want to study some kind of random object which is a limit of these coalescing random walks. What is it? You certainly don't want to take that subset of space-time which consisted of the paths and take the limit, because you just get everything. So how do you think of it? Choose a reasonable space. That's analogous, roughly speaking, to choosing space of continuous functions for studying single Brownian motions. And then gets characterization of the object and weak convergence results based on the characterization. So let me say that this choice of the space is motivated by the approach of Michael Eisenman to scaling limits in models like percolation. In percolation, you have you don't have, say, two-dimensional percolation. You don't have space and time. You have two-dimensional space, and in the discrete system, you have critical percolation on some lattice, so you have certain open curves or paths within the lattice, and you want to study scaling limit in which the lattice spacing goes to 0, and he proposed an approach to that in which the basic objects are, again, it's a mistake to look at the set of open paths as a subset of R2. You somehow should focus on the collection of paths themselves. So that's basically what he proposed, that you consider the random object as a random collection of curves of some sort. And we do the same thing, except our curves are rather simpler because they're really graphs of functions in space-time. So it's one-dimensional functions of time. But the idea of treating the object as a collection of paths really goes back to Eisenman, and that was done in more detail so the technical details in the sort of, not the space-time version, but the spatial version are done by Eisenman and Burchard, and then there was another paper of Eisenman, Burchard, myself, and David Wilson, where those ideas were applied to spanning trees. So the basic point is that the space that we use is that we want to look at the random object as something which is a random set of paths, and to get the sort of machinery in motion in order to do a usual sort of machinery of weak convergence of probability measures, then you need to choose sets of paths where you have some kind of decent metric space structure on the sets of paths. So that makes it a little bit complicated, but the basic point is that you should think of the object as a random set of paths. That was not the approach of the early work of Arati and Toth and Werner, which was more in the spirit of ordinary kind of stochastic processes, and so we think that this approach is somehow more natural. So let me get a little bit more. I'm obviously not going to be too complete. I guess in this talk I'm not going to prove anything, and I'll be happy if I even can state some things more or less precisely. But I'm not going to be that precise because but I'll try to give you the basic ideas. So a value of our random variable will be a set of paths. What is a path? A path is a graph of a continuous function. I do the time going up. It's a graph of a continuous function of time with a particular starting point. So you have to specify the starting time and therefore the starting location in space-time, and then you have some function starting at t0 going on after that. So there's an example of a path. Starts somewhere and then it's a continuous curve. That's a single path. We want to have we need some metrics around to do some analysis of things. And the metric, first you need a metric between two different such paths. The metric is basically a soup norm, except that, it would be a soup norm except for two things. One is that if the two paths start at slightly different times, you have to have something to take into effect the difference of the times. So it's a kind of a soup norm with doing something or other to measure the difference in starting times. So things will be close if the starting times are close, and if the paths are close after both have started, and when there's only one, when only one exists, it hasn't moved too far away from where it will be when the other one starts. And the other difference is that for technical reasons, we would like to compactify space-time because we basically want to say that two paths which are both very far away from the origin in either space or time, say both very far to the left in space and either direction in time, but we don't care very much about those. So we do some compactification of space-time to take that into account. But basically, it's a soup norm on the paths. And now our real object is a collection of paths, and the collection of paths that we work with are collections of paths which are compact subsets of this space pi. So a random set of paths is something which, for each omega in a probability space, its value is a certain collection of paths which altogether form a compact subset of this space pi of paths. So an example of that would be the set of paths from coalescing random walks. All possible paths in all of discrete space-time from the coalescing random walks, that will be a compact subset of pi. We also need to, because we want to work with random variables whose values are sets of paths, we need to say how close is one random variable to another. We need to say, therefore, what's the distance between two sets of paths. And that distance is the induced Hausdorff metric on this space coming from this one. So that simply means that two sets of paths are close, two compact sets of paths are close if every path in the first set, there's something close to it in the second one, and vice versa, which is about the most natural thing you could do. So that's the space. The random object, both, you don't need to do this for the coalescing random walks, but this is extremely useful for the limiting object, is a collection of paths, a compact subset of paths, and there's this natural metric on those compact subsets. So both the coalescing random walks and the Brownian web itself, the limiting object, will be random variables taking values in this space. So a realization of the random object is a compact set of paths. In particular, the realization of the Brownian web, a single Brownian motion, its realization is a continuous function of time. A realization of the Brownian web will be a whole collection of continuous functions starting from many, in fact, all space-time points, and as we'll see in a little bit, with multiple ones from some space-time points. Okay, so that's the space. What about the characterization theorem? Well, let me walk you through this characterization theorem. There are two conditions. The first one, which actually hides several conditions that are thrown together, and that's condition 1, and then condition 2. Condition 1 is the sort of what I call the obvious one. Condition 2 is not so obvious. So let me give an example again with just ordinary Brownian motion. So ordinary Brownian motion, the characterization theorem is if you have a random variable whose values are continuous functions, then it has the Brownian motion distribution, namely the Wiener measure, if you know that the distribution of the values at any finitely many chosen time points are given by Gaussian variables with certain covariances and certain means and covariances. So the analog of that here is specifying the starting space-time points. We have a collection of paths. Pick 5 space points in space-time at your leisure and ask, well, what can you tell me about the paths that start from those points in this collection of paths? Condition 1 says it is is the analog of in a single Brownian motion saying that you have Gaussian variables at certain values. Here, what you're saying is from those 5 space-time points, first of all, with probability 1, there's only one path from each of those points. These are kind of deterministic space-time points. Each one of those by itself is distributed like a Brownian motion, starting from that point. And altogether, those 5 things are distributed like 5 coalescing Brownian motions. After all, we're doing an object which is supposed to formally correspond to coalescing Brownian motions starting from everywhere. So if you pick 5 points in space-time, you should have 5 Brownian motions from those 5 points which coalesce. And that's what condition 1 says. From each one of those 5 points, deterministically chosen, you have a unique path, and those 5 unique paths are distributed like coalescing Brownian motions. So if you were arguing by analogy with single Brownian motion characterizations, you would think you'd be finished here. But in fact, you're not, because it turns out that there are, and this goes beyond this talk, and actually goes somewhat beyond what's actually been done, but completely. But anyway, it turns out that there are perfectly natural random processes which one can get as scaling limits of other things that I haven't talked about, in which the limiting object also takes values in the same space where a realization is a set of paths, and it satisfies condition 1, but is not the Brownian web that we're talking about that you get when you take the limit of coalescing random walks. There needs to be some extra condition telling you that that you don't have that other kind of object. And roughly speaking, the there are various versions of the second condition. This is one particular one. All of them have the property that they tell you that what you have besides these paths that you get from 1 is nothing else other than what's forced you from 1, right? Since your object is a compact set, particularly closed, all the limits of paths in here must also be in the object. So you have all these paths from kind of deterministic starting points and their limits. And the second condition in the various versions of it tell you don't have anything else besides that. One particular version is this one, which has to do with looking at a sort of a counting variable. You take a particular time t0, some later time t0 plus t, and you look at all the paths which pass through, which are in existence at time t0, either from before or just starting there, and follow them as they coalesce and ask how many of these coalesced paths pass through a certain fixed spatial interval at the later time t0 plus t. That's a number variable, it's a counting variable, and one way of ensuring that you don't have any extraneous paths other than the ones that you're forced to from condition 1 is to say something about the distribution of this number, and it turns out to be enough to give an exact value for the expected number, which it has a simple formula like this. This counting variable is eta hat. That variable will also come up in the convergence theorems. Okay, so let me kind of quickly go through a few more things. I think there's something, I know this is a little bit technical, and so I'm going to kind of skip ahead to go to something that's less technical and a little easier to absorb. The special case of our convergence theorems is that indeed, if you do the diffusive scaling of the coalescing random walks, that converges to the Brownian web in the natural sense. Once you've chosen your space that you're working on, as we did before, it has the Borel-Sigma algebra associated with the metric, and you have weak convergence in the normal sense for that situation. And there's a general convergence theorem, which I think I'm going to skip over, whose conditions involve these variables eta hat. It can be applied to the coalescing random walks, and you get convergence for the coalescing random walks. Okay, let me skip on to one last transparency, which I think is interesting. Which involves some properties, much of which was already done by Toth and Werner, which I'll call zoology and duality. So the zoology is discussing different space-time points. How many paths of different sorts are there associated with such a space-time point? So a kind of generic point, by that I simply mean pick some non-omega dependent point, kind of a deterministic point. You pick it in advance without looking at the realization of the process. Then there is a part of that condition 1 is that there's a unique outgoing path from that point. It's distributed like a Brownian motion. And it also turns out that there is no, with probability 1, there is no incoming path. If you remember back in the random walks, there were lots of points where things started from there and there was nothing earlier. So this is the continuous space-time version of that, and that's generic. So generically, there's a single path distributed like a Brownian motion starting from that point, and nothing earlier that passes through that point. That's a generic point. On the other hand, there certainly are points where there are things starting earlier. For example, if you take this green path and look at any point on it, then there's something starting earlier, namely the green path itself. So there are certainly points where you have one thing coming in and one thing going out. There also are points where green paths coalesce, where there are two things coming in and one thing going out. Okay, so all these cases are sort of clear. So then you can ask, what other possibilities are there for numbers of things coming in and numbers of things going out? Well, it turns out that the other possibilities besides nothing in, one out, one in, one out, two in, one out, are nothing in, 2 out. That actually happens. You can pick a time in advance deterministically, and this happens at a dense countable set of spatial points at that time. You can also find places where there are 3 things out and nothing in. To find these things, you have to pick not just the spatial point in an omega-dependent way, but also the time. These are much less generic. And the most interesting case is one where there's 1 thing going in and 2 things going out. The reason this is interesting is that in the space of curves, which is what we're really working with, the space of paths, there is a path which starts earlier and goes through this point. The one that goes through this point continues on one of these 2 things, but not on the other one. So one of these 2 actually starts at that point. The other one is a continuation of something earlier. You never have anything where you have both continuations. You don't have any real bifurcations. You have kind of things that look like bifurcations, but which really aren't. And there's nothing else. These are 1, 2, 3, 4, 5, 6. Those are the only possibilities. There are no other possibilities. There's also very interesting a dual set of paths, which you can get the following way. Suppose you take a generic path. Here's the outgoing curve here. If you look earlier in time than that starting point, the paths starting earlier will coalesce with this thing eventually. Everything always coalesces eventually. Some of them coalesce from the left and some coalesce from the right. So there's a kind of separatrix between those locations where things starting on one side of this curve here coalesce with this thing from the left, and from the other side they coalesce with it from the right. That separatrix is a sort of dual path, and it turns out that the set of all these dual paths, at least if you take their closure, by itself forms a Brownian web, but going backwards in time. So the actually real natural object is to study the green forward paths and the red backward paths all together, and those have sort of interesting structure. This is what this thing over here, which had 1 thing which continued and 1 thing which really started there. If you look at the dual structure around there, it looks like this. This one goes, it's the same. The dual thing has the same sort of structure. There's the dual one, there's one that goes through, and there's another one which starts there. Anyway, so there's, but all these things happen on lower dimensional parts of space-time. They're non-generic. Anyway, it gives you a flavor for why this object somehow is a sort of natural, interesting structure, and I guess I've gone over a little bit. Thank you.
Questions?
I ask you if it's possible to apply this model to study particle physics, decay of particle physics.
I don't know. We believe that it will be useful for lots of things besides aging. Aging was the context in which we got interested in it, but we think that it's somehow will be a useful object in various things in stochastic differential, one-dimensional stochastic differential equations. Whether there's anything to do with particle physics, that I have no idea.
At the very beginning, you only have directions going up or to the right. That shows right or
Well, when I rotated it, it was going right or left.
Suppose you had 1/4 probability, and you have the 4 directions. Then you would have paths where 2 guys can going in the same direction and sort of kill each other. In your case, you don't have that problem. For things, you can always continue and you have coalescence, but you don't have sort of...
Well, okay, let me make a comment which I'm not sure is precisely answering your question, but if you study the Q equals 2 voter model with 2 colors, which is the standard one, then if you study the boundaries between regions of the same color in that model, those boundaries actually do annihilating random walks. However, that model still turns out to be related to coalescing walks, but it's related to dual coalescing walks. So annihilating random walks and Q's that are bigger than 2 but less than infinity sometimes annihilate and sometimes coalesce. Somehow all those things are, in some sense, contained in the coalescing random walks if you study, look at the right quantities. So the coalescing walks, it somehow turns out to be more general than annihilating walks if you look at it right.